On behalf of 24houranswers.com, I welcome you to today's lesson. In this video, we're going to look at an optimization example that deals with minimizing the material to make a cylinder. A cylindrical container is to be designed and mass produced such that it holds 1 gallon of water. 1 gallon of water is 231 cubic inches. That will be helpful in a moment. Given that the side of the container and the top and bottom will be made of the same material, what should the height of the container be to minimize the amount of material needed to mass produce this product? We have a cylinder here. The volume of a cylinder is pi r squared h. But then we also want to do something with minimizing the amount of material needed. Volume, we're not going to minimize volume. We know exactly what volume we need. We need 231 cubic inches. So therefore we have 231 is equal to pi r squared h. When we start working with the radius and the height in this problem, the radius and height will both be in inches as well since our volume is in cubic inches. If we're talking about minimizing the material to make this container, we're talking about the surface area of this container, this cylinder. We have two circles that are the same. The area of one circle is pi r squared, so the area of two circles will be 2 pi r squared. However, we have to talk about the side of this container, the side of this cylinder. If you remove the top and the bottom, and then you were to take like a pair of metal cutters or something, and you were to cut down through the side of this container, and if you rolled that out flat, you would have a rectangle. This rectangle, this piece right here, would be the piece that joined up over here where I had this dotted line. That is the height of the cylinder. This length here is actually the distance around this circle because we rolled this out flat once we remove the top and bottom. The distance around the circle is 2 pi r because that is the circumference of the circle. So now we have a rectangle that's actually the height of the cylinder, and its length is the circumference of this circle up here. To find the area of this rectangle, which is the side of our cylinder, we take 2 pi r times h, so that is 2 pi r h. That's going to be the extra area that we need for the surface area. This is going to be the formula that we want to differentiate. However, we do have surface area in terms of two different variables, a r and a h. Let's just get this h right here. Let's replace that with something in terms of r. We can do that by going back to our volume formula. If we take 231 and we divide by pi r squared, really what I'm doing is I'm dividing by this pi r squared over here, and that's going to give you h by itself. This is beneficial because now we can take what h is equal to and we can substitute it in right there. And notice that h is equal to something in terms of r. That's going to give us this formula in terms of r. Therefore, when we substitute that into h, that's exactly what I've done here. We have 2 pi r squared, I brought that on down, plus 2 pi r h, and then substituting what h was equal to from our volume. Now we can clean this up a little bit by canceling out the pi's. We can get rid of one of the r's in our denominator, and then I'm just going to move this r up to the numerator to help with differentiating, and that's going to make it r to the negative 1. And that's exactly what I've done here. I brought down the 2 pi r squared. 2 times 231 is 462, and then that r to the negative 1. Again, we had a r to the first in our denominator. I just shot it up to the top. This is going to help us with differentiating. The reason why we want to find the derivative of this is because we are trying to minimize the amount of material. Material needed to make the cylinder is going to be surface area. Therefore, S prime is equal to, pulling this 2 down and multiplying it by that 2, we have 4 pi r to the first now. Just going to write an r there. And doing the same thing with our power rule here. Negative 1 times 462 is negative 462, and subtracting 1 from our exponent, we have r to the negative 2. Let's now set this derivative equal to 0, and I'm going to also clean up or rewrite this second piece over here. I'm going to write it as 462 over r squared. Because now we have a fraction, we can multiply all of our pieces in our equation by r squared to get rid of this fraction. Multiplying 0 by r squared, we still have 0. Multiplying r squared by 4 pi r gives us 4 pi r to the third now. and then multiplying r squared by this, we'll simply get rid of the r squared in our denominator, and now we can solve this remaining equation. Adding the 462 to both sides, we have 462 is equal to 4 pi r cubed. And then if we divide by the 4 pi on both sides, we will have 462 over 4 pi is equal to r cubed. Sure, we could simplify this if we want, but if you recall, I'm going to go back up in a minute and show you, we're trying to find the height. So I'm just going to go ahead and get this radius by itself by taking the cube root of r cubed and the cube root of this side as well. Therefore, our radius is equal to the cube root of that stuff. I'm not really worried about simplifying it because we're going to be substituting this back in right here in a second. Now you may say, let's just go ahead and type that in and get an approximation. There's really nothing wrong with doing that, but I'm a big fan of not using any approximations until my final answer. So going back to the problem, it says, what should the height be? Well, this is the radius, but recall earlier in the problem, we got the height by itself, so we can take this r value. R is equal to this stuff. We can plug it in right there to find our height to answer our question. And remember, since we were dealing with cubic inches for our volume, radius and height are also going to be in inches. And that's what I've done right here in the calculator. We have 231 over pi, and then we have our r value that we got from here, and then I'm squaring that radius. So if we do this, we get somewhere right around 6.7 inches. And again, this type of problem can be beneficial to companies who are mass producing products, such as companies making soup cans or something like that. They want to be able to fill a can up with a certain amount of product, in this case water, but they want to fill it up in such a way that maybe they can use the least amount of material to make that particular can in this case. There are many combinations of heights and radii that can give us this same 231 cubic inches that holds 1 gallon of water, but as long as the height of our container, the height of our cylinder is 6.7 inches in this case, that's going to require the company to use the least amount of material to make a single cylinder. And that's it for this video. I hope it helped. Be sure to check out our YouTube channel for more videos. Links to our social media are in the description below.